Hey there, explorers. Welcome back to MJ School of Mining and Geology, your go-to place for all things geology. Today, we are diving into the fascinating world of minerals and how they mix and match to form something truly special. Have you ever wondered how two different minerals can blend together to create a whole new rock? Well, that's exactly what we are dealing with today, solid solution system. But I want you to imagine yourself in a kitchen and then you're trying to mix the ingredients to bake a cake. I mean, ingredients such as flour and sugar, and then you have to combine these ingredients in a precise ways to create something delicious. Now, imagine doing this with minerals inside the earth. This is what we call a solid solution system, and it's all about how different minerals can blend at various temperatures and compositions to form new structures. So, stick around because we're about to dive deeper into these diagrams, exploring the specifics of how albite and anorthite create a range of plagioclase minerals. Don't forget to like, subscribe, and hit the bell icon for more geological adventures. Let's get started. So a phase diagram is a graphical representation of the equilibrium relationship among two or more phases, typically as a function of one or more intensive variables. So when we talk about intensive variables, we're gonna be talking about temperature, pressure, and chemical composition, but most especially temperatures and pressures. So if we're gonna see when we're going to be looking at the Gibbs phase rule, if we're talking about only one intensive variable, we have to put one. But if we have got temperature and pressure, or then we have to put two. Okay. Now, in the phase diagram, we also have what you call a system. So a system is just a mixture under observation. So if, for example, if we're talking about the albite and anorthite, okay, and then the system, it will be albite anorthite system. Okay. And then the component is just the number of chemical entities, okay, required to describe the composition of a phase that exists in a system. So if we're considering what you call the albite anorthite system, then the end members will be the albite, and the components, will be the albite and what you call the anorthite. Okay, if we're looking at the anorthite albite system, right? And then the phases, it will be the crystals and also the liquid. Okay. So the other thing that we need to understand is what you call the phase rule. The phase rule, or the Gibbs phase rule, it has this formula over here. It is this formula over here, where C is the component, and then P is for the phases. Then this is for the intensive variables, because here we'll be talking pressures and temperatures, which is what we put in two. But if we were talking about only temperature or pressure, we're going to put one here. Okay, this is now the degree of freedom. The degree of freedom is just what we call the number of independent variables in simple terms. And then, but now this number of independent variables, they must be specified, okay, in order to define what you call the state of a system. They must be specified to define the state of a system. When you talk about the state of the system, the system can either be invariant, it can either be univariant or divariant. So if the degree of freedom is equals to 0, then we say the system is invariant. But if it's 1, we say it's univariant. But if it's 2, it's divariant. I mean, units 1, 2, it's di. Okay. Now, remember, we need to define the state of the system. So if the degree of freedom is 0, then we say the system does not move. So the system does not move. It means we have got more number of components. It means we've got more number of components or phases, okay, which are were added to the system. So the system now, it won't move because we've got more components or more phases. The system, it won't move. Then how do we make the system to move from being invariant to either univariant or divariant? It means we must consume one of the phases, okay? Until now we start to have less of the phases, then the system can now move. That's what we call the degree of freedom, okay? And this, the degree of freedom, it's very useful because it tells us about the state of the system, okay? Now, let's now talk about lever rule in what you call phase diagrams. Lever rule, there's got the same analogy with what you call physical lever, okay? Showed by these two guys over here, or I think it's maybe a guy and a girl, maybe they're in the park playing, yeah. So it has got the same analogy with what these people are using now. That's what you call a physical lever. Remember, you have to balance the physical lever, okay, by adjusting the length. Right, by adjusting the lengths of what you call of the lever arms, right? So in the sense, or in the case of the phase diagrams, the lever rule, it is used to determine the relative amount of the phases present. The relative amount of phases present. So if, for example, I want to know the proportion of liquid and what you call the solid, okay, or the crystal. So if I want to know how much of the crystals do I have and how much of the solid do I have, we use what we call a lever rule. I hope it makes sense. Okay. Moving right on. All right. Let's now talk about the real stuff. Okay. Say for instance, let's start with the fact that our on our phase diagram, okay, and we need to define firstly what we call a system. We need to know what are our components, and then we need to know what we call our phases. Okay, so our system is what we call albite Albite system. Albite Albite system, and the components we've got, just allow me to write, in abbreviate them, and then we've got albite and, sorry about that, and Albite as components, and the phases we've got solid and the liquid, or we've got the crystals and the melt. Before we could analyze, we should know our system. All right. Then now, on our phase diagram, we have what we call the liquidus line. We've got this line, what we call a liquidus line. So above this line, our mixture is completely melted above this line. So that's why we have the phase of or the region of liquid only. So above the liquidus line, we are in the region of only the melt. But now below the solidus line, we are in the region of completely, we're in the region where we have only solids. Okay. Now, below, between these, okay, in this region, white regions, that's where then now albite and anorthite, they are coexisting. Okay. They are coexisting. So so it means between now these, like, we have got liquidus line and solidus line. So it will mean between these lines, where everything is completely, between these lines where everything is completely solid and everything is completely solid, we have what you call pure end members coexisting. Okay. Now, if we're considering the pure end member albite and the pure end member anorthite, here at the temperature of, sorry about that, it should be 53 degrees. So at the temperature of 1553 degrees and 1118 degrees, that's the temperatures, the exact temperatures where the pure end members start to melt. So you must always keep it in mind that your pure albite will melt at a temperature of about 1118 degrees Celsius. Okay, and then the pure anodite will melt at a temperature of 1553 degrees Celsius. Now, non-end members, okay, that in the field between pure albite and pure anodite, they would not melt at one temperature, but they would melt over a range of temperature. That is the temperature between 1018 degrees and 1553 degrees. That is the range of temperature through which the non-end members will melt. That's one thing, or the first thing I wanted to bring to your attention. Now, but all right. So we start with what you call bulk composition. So let's say we have what you call X here. It's our bulk composition. Bulk composition is what we start with. So if we check over here, we've got 0, 10, 20, 30. We've got 30% of anodite. We've got 30% of anodite. And then, of course, we've got 70% of the albite. That's what you call the bulk composition. Now, if let's say the bulk composition, it was happening around 1,500 degrees Celsius. But if we were to lower temperature to somewhere around this temperature, okay, so I think it's 1,400 degrees. So somewhere here, if you lower the temperature there, that's where we're gonna have what we call the first mineral to form. Okay, as X cool. So as X cool to this temperature of 1,400 degrees Celsius, will start to form new crystals, or the new or the first mineral will form here. But now, don't forget that I want to bring this to your attention that if you want to know the crystals, the composition of the crystals, they are read along what you call the solidus line, but the composition of the liquid are read along the liquidus line. That's one thing I want to bring to your attention. Now, because the first crystals they started to crystallize here, then how do we read their composition? Because it's the crystals, then we must go towards the solidus line. Then, but here we don't see any numbers. Then how can we now read the composition? We go, sorry about that. I won't be able, because of my orientation, I won't be able to make a straight line, but somewhere around there. Maybe let's say 75%. So, and then it means then the first crystals, they would have around 75%. They would have around 75% anodite. Okay, the first crystals, they would have around 75% anodite. But now you lower the temperature to around 1,300 degrees Celsius. So when we are here, when we are in this red circle, then we can't directly say I have let's say 10% of the liquid or 20% of the solid. No, then because we are in the region of the, or we're in the white region. So here, when we are here along these regions, we must always use what you call the lever rule. We must always use what you call the lever rule. That's where we apply the lever rule. Then how do we go about that? Now, the formula of the lever rule, if we want to know the percentage of the solid, or the proportion of the solid or crystals, we must always now agree the solidus line is this line. So if we want to know the proportion of the crystals, we go the opposite direction. So the opposite direction is in the direction where we are intersecting with the liquidus line. So it means, let's say this is OA, this is OB. So it means now if we are in the other direction, we'll take the direction OA. okay, OA. So we'll say OA, then divide by OA plus OB. Okay, so if we want to the proportion of the solid, we go the opposite direction, we say OA. But if you want the percentage of the liquid, okay, of the melt, then the melt is this way, then the opposite direction is that way. Say we have to say OB, then we'll say OB divided by OA plus OB, then we mustn't forget to multiply by 100, multiply by 100. Then that's how a level is calculated. Now, let's take a close look here. It becomes too messy. It becomes too messy. Let's erase these things a bit. Okay, let's erase these things a bit. All right. Let's change. Okay. Yeah. So we are here. Then we want to know something. We want to know something that we are here. We want to know how much of the solid we have and how much of the liquid we have. We use these formulas. Okay. So now check. If we want to know the percentage of the solid, then what do we say? We say OA. Then if we check over here from here to here, it's about 15 units. Okay, because let's check is let's say it's 5, let's say it's 5, 10, it will now be 15. All right, it will now be 15. So we'll say the percentage of the solid, it will now be 15 divided by then 15 plus. Then what is the distance from here all the way to here? It's around 25. It's about 25 from here to there. It's about 25. Okay, then you'll say it's 25 multiplied by 100, which is why over here we say the crystal fraction, it's 15 divided by 15 plus 25, and then which is about 37.5%. Okay, so but now when we want the melt, when you're looking at the formula, it's OB is this way. So from here to there, okay, from here to there, let's check, is 10, 10, okay, 10, 20, 25, yes, 10, 20, 25. So what about that? Yes, it's 10, 20, and 25. It's OB, and then here it's 15, which is why at first we said 15 plus 25, because OA it's 15, and then OB is 25. I hope you understand. Then now with this one, you say for the melt, you will say 25, because OA for the melt, sorry, you have to say OB first. Okay, for the melt, you have to say OB first, which OB is about 25. Then you say the percentage of the liquid is just 25 divided by 15 plus 25 multiplied by 100, which is about 62.5%. Now it means when you are somewhere here, okay, you are somewhere here, you are having 62.5% of the melt and 37.5% of the crystals of the plagioclase. I hope this makes sense. Okay, don't forget that when you're using the lever rule, you are kind of doing the opposite. So if you want the proportion of the solid, you say the solidus line is this way, and then I have to go the opposite line, which is this way. Okay, so you just do that. I hope this makes sense. Okay, but now let's check what we call, let's keep checking what you call the crystallization history. Okay, let's keep checking what you call the crystallization history. Remember, we were somewhere here. Then let's say we're to lower now the temperature to this point. Okay, if we're to lower the temperature to that point, then we ask ourselves, what is the composition of the last mineral? What is the composition of the last mineral to form, or the last crystals to form? The last crystal to form, remember I said that the composition of the crystals, we read it along the solidus line. So it's exactly here. It will have 50%, it will have 30% of the anorthite. It will have 30% of the anorthite. That's exactly what we know. Okay. But now let's check the last composition or the last melt, okay, that we have. What would be the composition of the last melt we have? Okay. Then now the last melt would have somewhere, remember the melt composition is right along the liquidus line though. So we have to go this way. We have to go this way. And look, around 5%, somewhere here, around 5%. I hope you understand what we're trying to say. It will be, I think, around 5% of the anorthite. Okay, so we move now to apply all these things. Okay, I hope now you understand. So this is for you now just to also practice again that if you are somewhere here, then you can apply the lever rule. Sorry about that. You can apply the lever rule, and then you now find that the proportion is between 45% and 55%. That's the proportion of the solid and the liquid. Okay, so now let's deal with this example wherein we are having the bulk composition of 50% albite and 50% anorthite. And then we ask ourselves the following questions that, for example, how many faces are present in figure 1? Remember I said you should know the faces, you should know the components, and how many components, okay, with their names, and what is this system. Okay, I mean, we have got two faces, which is we've got two faces. So we've got here we have got two faces. We have got two faces, that is to say liquid and the solid, okay, or the melt and the crystals. And then how many components? In terms of components, we have what we call the albite. We've got what we call the albite and the anorthite. So we've got two, and then these are called albite and the anorthite. And then how many? What is the system? The system it's albite, albite, albite anorthite system. Okay. Now, what silicate group do these minerals belong to? You know, they belong to tectosilicates. So because we know tectosilicates, we've got two types of tectosilicate groups. We've got the quartz, and then we've got the feldspars. And then the feldspars, we've got this diagram, K, sodium, and calcium. Then the feldspars that are between sodium and calcium end members, we call them the pledge. Okay, and then these ones we call them the alkali feldspars. Okay, and then how can you optically and physically, you know, identify the alkali feldspars? You will see what you call X solution lamellae. You will see what you call X solution lamellae, and then these ones, especially optically, you will see what you call a polysynthetic twinning. We will see what you call polysynthetic twinning. Okay, okay. Yeah, I hope you understand that. And then so these feldspars, because we've got the calcium rich end member and then the sodium rich end member, then we know we have having what you call the plagioclase. Okay, these are the plagioclases. But now we want to know what silicate group do these belong to, and then they belong to what you call tectosilicate. But now what other varieties of K feldspar exist beside orthoclase? Because you know, remember, we know that this is becoming too messy. Let's erase them again so that I can show you the diagram nicely. Okay. Yeah. So I'm sorry about my background. It's still during the day where everyone is still around in the department. My apologies. So we know that here we're having what you call a microcline, And then the blue variety of a microcline is what you call Amazonite. All of these things, they've got these exsolution lines physically and optically. Okay. And then we also have we also have what you call the orthoclase, and then we've got some things here. We've got some things here, and then we've got cyanidine over here. Okay. Then remember these end members. We're talking about oligoclase, cyanidine, bitonite, labradorite, and many others until we have got what do you call it, the anorthite. Okay, so which is why we say, when we say what other variety of cave feldspar exists beside orthoclase, so it means we've got this cyanidine and we also have got this microcline. I hope it makes sense. Okay. Now, all right, let's move on. So what is the composition of the first mineral to form as X-core? Okay, as X-core. Remember, we've got this bulk composition where we're having 50-50, 50% of albite and 50% of anorthite. So we lower the temperature to this A, and then the first crystals will form here. But where do we read its composition? We say the crystals, we read their composition along the liquid solidus line. So we go here and then we go a bit downward. Okay, so I think it's somewhere around, so I think it's what is the yes? I think it is 90% of the anorthite. And then what is the composition of the last mineral to form as X-cores? I mean, we'll go downward. When we get somewhere here, if we were to stop here, then we need to use lever rule to know the proportion of the solid and the crystal. Then we go a bit down, we lower the temperature somewhere here, okay, somewhere here to around, I think, 1226 degrees, somewhere here. And then this is where we're gonna get what you call the last mineral to form. Okay, so because we are talking about the crystal, where do we read the composition? Along the liquidus line, so along the solidus line. So it means it has what you call 50% of the anorthite. Remember here we said it's cyanidine and what we call a microcline. And then here we said they are tectile. And then, yeah, I hope you understand. What is the composition of the last liquid present as X-cores? Okay, so the liquid, okay, along the same temperature, the liquid must be somewhere here, which is around, let's check, somewhere around 9, because it's not 10, somewhere around 9%. So we'll say 9% of the anorthite. Then when the liquid reaches the composition C here, remember the one thing that I want to bring to attention is the liquid composition changes along the liquidus line, whereas the solid composition changes along the solidus line. So we know immediately when we start to crystallize the anorthite, okay, the liquid composition changes along the liquidus line. Now, it changes until it reaches C. So we want to know when the liquid reaches composition C, how much liquid is present. But because the composition, we read it along the liquidus, yes, but because we read this thing along the liquidus, then what do? We would say okay, sorry, okay, we are here. Okay, we are here. We want to know when the liquid reaches composition C, how much liquid is present. Okay, so how much of the liquid is present? It will be plus minus, let's check. Okay, somewhere around 38. Okay, when the liquid reaches composition C. Okay, we want to know how much how much liquid is present. No, we don't want, sorry about that. We don't want to know the composition, because this will be the composition, but we want to know how much of the liquid is present. So we have to go here, and then we say it's about 82%. Sorry about that. We have to say 82% liquid. So because we don't want to know what we call the, we don't say, on the question doesn't ask what is the composition. Okay, we just want to know how much of the liquid do we still have when the liquid reaches composition C. We'll have about 82%. Okay, we'll have, sorry, it's here, man. It's here. Yeah, so it will be around 82 or 83%. So then, over what temperature range does X crystallizes? Okay, so it's a bit messy. Let's try to calculate that. When we say the temperature ranges, remember the temperature, it increases from bottom to the top, so it goes this way. Okay, so but sorry, decreases. Okay, going downward. So it means temperature, for us to calculate, we have to check vertically. So that's A. Over what temperature ranges does A crystallize? A, it's here. Okay, so let's check vertically. A at this temperature, we go straight like here. Here it's about let's say 1420 degrees and Celsius, and then we subtract that from let's check over here. Okay, remember the last crystal of A, it will be here. Then we go and be like, also it's somewhere around 1226 degrees Celsius. So let me press my calculator. 1420 minus 1226, it gives me somewhere around 206 degrees Celsius. So then A will crystallize over a range of 206 degrees Celsius. Okay, so I hope this lesson was helpful, especially what we call the albite. Sorry about that. Especially what you call the albite, anorthite system. So thank you guys for joining us today. Your support, we really appreciate your support. And then if you have any topic you'd like us to cover in our next session, you are more than welcome to drop your comment in the comment section. And please don't forget to like, share, and comment. And then when you don't understand, you are more than welcome to ask me 24/7 in our comment section, or you can also send me the email at what we call malibati moraka at gmail.com. And then when I have time, I will be pleased to respond. All right. So the next session in phase diagrams, we have to talk about what you call the eutectic and peritectic points in phase diagrams, and then with examples. Okay. So I would like to say until next time, cheers.